Okay, folks. Welcome to the second to last class of the semester. Woo woo! Anyone freaking out? Didn't realize it was last week. How's that? Doesn't feel like it. Doesn't feel real. It's like 16 weeks flies by. At first, it's a slog, right? You're like, ah. And then you get towards the end and you're like, fuck! Okay. So today, we're going to have one of the last chapters of content. David's going to tell us about random numbers and how we generate them and how we use them. I was hoping that Saul would be here because that's what his project is on. But hopefully he will arrive and have really good answers to our questions in the question segment. And then on Wednesday, Trinity is going to wrap up everything we've ever done. Yeah. Right? That's the plan. And Trinity is going to do a great job of just sort of giving us a broad overview of using the tools that we've learned in this class. And then next week, there is no traditional class. There won't be like time to come in. But I would like for you to, work with me, ask me questions, office hours, that type of stuff. We will have class at the normal time on Wednesday, as long as no one has a conflict for a final. So I've asked you all to check that. And then we'll do presentations. And I will put up a little form at the beginning of class of who wants to go in what order. You will be allotted something close to 10 minutes. If you each get 10 minutes with a couple questions, that gets you close to 120 minutes just on talks alone. Now, I know that not everyone will be doing presentations because not everyone will be turning in their projects. So it's probably closer to 100 minutes. You take some questions. Think about 15 minutes worth of you standing. Is that okay? Has everyone here created slides for a talk before?
Yeah.
Okay. So you're all professionals. Okay. Well, let's remember that this is a low stakes presentation. That is not to say there are no stakes. There are low stakes. You're presenting to your colleagues. So you want to make sure that it is a nice communication. This is an effort to hone your communication skills. And I am hoping that, some of the presentations we've done so far, being a little more self-led, that you feel comfortable talking about the material. If you don't feel comfortable talking about the material and you want to practice it ahead of time, you're welcome to come chat with me and I can give you feedback on it beforehand. What I don't want to see is I don't want you to go up there and never practiced it, never done it before, and you're done in 3 minutes. Okay? You should take 10 minutes to explain your project. I also do not want to see your code. I don't want you to pull up CoCalc and be like, here's what I did. That's not a presentation, right? You want to present the motivation. You want to present what you did, what the basis for that choice was. And in a lot of cases, it'll be much like the homework that we're seeing, where I'll give you an equation and ask you to chart something, right? Or plot something. But just leave the code out unless it's really important that you demonstrate, hey, I did this thing. This is kind of unusual. This is unique. And here's how you can implement it at home, right? Okay. More of that detail is on Canvas. You read the thing on Canvas? Go reread it. Okay. How's everyone doing? Okay. So, David is going to present. And do you want to present from your computer right now, or do you want me to put this up and you can talk to it and then we can switch later?
So I could talk from here.
Okay.
Pretty much my whole talk is just the code on screen.
Okay.
So we start off talking about random numbers, and we get this equation at the start of chapter 10.1.1, which is x prime is equal to ax plus c mod n. And what this does is kind of try to simulate random numbers, but we can kind of tell that it isn't random because if we know the formula. then we know what the outcome should be. Everything like A, C, and M are constants, where we just plug in different values of X. So going on from that, we yeah, we get our, I don't know what to call them, pretty much the things that we run to get random numbers, like the, I guess, function random, it'll print out a random float, and rand range, it'll print out a random number from the range 0 to whatever you put inside -1. So for example, when I ran it with rand range 10. So it'll give us a random number from a random integer from 0 to 9. The next one would be rand range m comma n, and that'll give us a random integer from n to n-1. In my case, I ran 1 to 10, and it'll give us one from 1 to 9. And then finally, we have rand range mmk, where it'll go from a random number from n to n-1. I ran it with 1 comma 10 comma 1. K will be our step. M will be the start, or like, I guess the first one. So if I did it from 1 to 10, it'll give us a random number, or random integer from 1 to 9.
Okay, so let's pause here for a second. Random produces numbers. Random, just with nothing in it, goes between 0 and 1. How are the numbers distributed? Randomly. What does that mean, randomly?
It means an outside source won't know, but the inside source will.
Means we can't predict it, right? Randomness means is trying to tell us that we should not be able to predict it. If it's a computer, is it truly random? Never. Never truly random, right? So this is how hackers get your information. All encryption can be broken. It's just a matter of time, right? So one thing that we want to keep in mind here is when we think about how are the numbers distributed, and we say the word random, right? There's different forms of random. So I was explaining with David, we were flipping a coin, right? You have equal probability of getting heads or tails, right? Now, is that all of the possible outcomes? If you flip a coin? No, what is the other outcome?
Lands on its.
Lands on its side. But the chances of that happening are slim, right? Very close to 0. So you'd have to flip it just so perfectly, or maybe you flip it and it lands in clay and it lands directly on its side, right? So the probabilities could change, and they may not always be uniform. Uniformity is the basis of what we're going to discuss today. And you really need to think about how random numbers are generated uniformly before we can get into anything weird. Okay?
So if we want to use that, let's say we want to use the random number that we get from using rand range, we'd have to set it equal to a variable. And then when we run it, it would use that same value in other places. Going on to 10.1.2, we talked about seeds. A seed is kind of like the start point of a sequence. Without it, we'll get a different sequence of numbers every time we run the code. And one thing that's really useful about seeds is that, let's say we're making a code that uses random numbers. If the numbers are constantly changing, then it's not really, we can't really tell if it's working or not how it should be. So using a seed prevents it from changing random numbers every time will let us they can go with that. So good.
Right. But notice here what the code did. So you run this twice, you get the same 4 integers. Yeah.
Why did the C input have 42? 42 would be start seed.
Yeah. Does it matter what the start seed is? So, David, do you mind explaining a little bit better what seed means in the context of like the oh fuck, what happened? Why is this being weird? Okay, in the context of say this equation. 10.1.
I believe our seed would be our penance.
Yeah, seed could be x here, right? So if these constants, right, are constant, then where you start is x, the seed. And the next number that you get is x prime, right? So if I start with the same seed, I should get the same digits every single time because it's a formula, right? There's nothing random. Yeah.
Variable now.
Oh, okay. Comments, questions, concerns before we move on? Are things truly random? On the computer? Not generally, right? Where is there a little randomness in the computer? Yeah, Anjali. Yeah, the electrons jumping around really are random. And what does that lead to? How can we see that on the computes? What? Yeah, but you're right. But like, is there something that we've talked about like we get as an output?
17th. We're talking about it's only accurate up to a certain.
So it's only accurate up to a certain point. That's the result of the fact that we have decimals, right? But that's not where the error comes in yet. That's not where the random error. In fact, it even has the word random error, right? What is the number 2 represented on the computer?
10.
Oh yeah, okay, you're right. You're right. That's for the code, the binary, correct.
Yeah.
But like for us, if I print out 2.0, is it always 2.0? Right. So Emmanuel just said 2.0000001 because sometimes that bit can flip, right? That would be a real example of randomness on the computer, right? Sometimes a bit flips because electrons just be doing electron things, right? Okay. Can we harness that for this part of the code? No. Because it's truly random, right? You can't both control randomness, control like harness it, and also ask it to be random, right? So it's either random or it's not. And so really what we're talking about is something called pseudo random numbers. Just like pseudo science. What? Well, pseudo just means sort of, yeah. Yeah.
Is radiation affected by like a Geiger counter? Is that truly random?
Great question. Saul? What? Oh, why me? Is radiation that is detected by a Geiger counter truly random?
No,
Why not?
because I mean it can double count, right? Talking about like the actual like experiment that we did here.
No, let's imagine that you have a perfect machine. And we're just talking about the radiation coming off of the cesium atom. Is it truly random?
The radiation case, the random.
Yeah, it's truly random. Truly. Okay. Fun, right? Do you know how the second is created? Like what our international standard for the second is? What?
I don't remember, but it's like the details and like it's really.
Yeah. So in order for our physics to be physics, we have to, of course, I'm sorry, I'm going to go on a tangent. My bad, David. So just tangent time if that's okay with everyone. So what's this? Is it? Ew, gross. All right, it's a meter stick. Ew, disgusting. Okay. So, so this is a meter stick, right? And from this, I can measure everything in the room, right? But let's say I keep using it, and it kind of gets ground down. And now all my measurements, well, they're just a little shorter than they should be, right? And all the things that we produce in here, let's say we're building tables, they're a little too short, and our customers get mad. So what do you do when your meter stick is not quite a meter? You get another meter stick. Good. How does that meter stick company that sells you the meter stick know how long a meter is? They define it?
Standardized, like, thing, like a bar that's like everybody can understand.
Okay, so there's a bar to meter bar that everyone has agreed that's what a meter is. The whole world said, okay, we believe you. Okay. And similarly, this bar is kept at a specific temperature because they know that it expands and it contracts. So at a specific temperature, to specific pressure, this object is this long. And we're going to define that as a meter, right? And you can find out all about this at what's called the National Institute of Standards and Technologies. And the second part you're quite familiar with, technologies. The first part is just as important. So now the question is, how long is a second? What? Because I can build something like this, right? That seems easy. How do you hold on to a second? What?
Someone chose, I think, like, some experiment happens in a second, and I use that instead of a bar.
Something happens in a second, right? And they choose that instead of a bar. And guess what that is?
No, like no.
Yeah, it's the decay of an element. So in fact, you can go, it's really fun. We'll do this after, so I'm getting disrupted. But essentially, we use a truly random phenomenon in order to define our standards. It's kind of fucking crazy. And they're called atomic clocks. Okay? All right. Um, Go ahead. 1.3? Oh, yeah, yeah, yeah. Where is it? Oh my God, what am I doing? There we go.
So 1.4 talks about probability and bias trends. Let's say you want to make a bias towards something. Well, first, there's one thing I forgot to mention about the random parenthesis. It'll print a random float between 0 and 1, but not including 1. So let's say we wanted to make a bias coin, so when we flip a coin, it would be biased towards one side rather than the other. The code says that if random is less than 0.2, print heads, else print tails. So every time this random is going to be less than 0.2, it'll print heads. Obviously, that's kind of biased because a point flip should be 0.5. So, yeah, that's pretty much all it is saying.
Yeah. Does process make sense? So this is the fundamental trick that we use for probabilities. You just look at the number that you randomly generated, randomly. Is it smaller or greater than some value? Okay.
And it goes they just use this same logic by defining all of their equations. And then in their main for loop, they have that same bias where you see for I in range NT1. If random is less than 2, then A plus
Good. So let's remember how decays work. Has everyone here taken modern? So what is the decay of an atom? What is happening? I mean, not like physically what's going on, but just when I say the word decay, what's happening? Yeah. Right. Yeah. So you have some larger nuclei become a smaller nuclei, or it changes something about it, right? Either a proton becomes a neutron, right? Or maybe it breaks apart, right? And in that process, the decay part, right? You always go from one number, let's say you start with 100 of that atom, to a fewer number of that atom, right? And so the important thing to keep in mind is this is just a counting, right? You're just counting the number of, for example, thorium atoms and the number of lead atoms. And if thorium decays to lead, then you have to subtract off the thorium atoms. And you cannot spontaneously generate them. So whatever disappeared from thorium has to be the exact same amount that is created from it. Okay. And by the way, if you want to know why you should be reading and understanding that example, it's because we're going to do 10.2 today. Okay, keep going. 10.5, this one? Yeah.
So far in chapter 1, we've been talking about subsetting functions. But there are a lot of physics problems. Most of it is non-uniform. So I can't really get understand. Sorry.
Okay. So how do we go from a uniform distribution to a non-uniform distribution?
Uniform is Gaussian, right?
No, uniform means even everywhere. So let me show you. I'm going to do a little drawing draw. It's going to help. Okay. This is X. Here's 0. Here's 1. Okay. What's the probability of getting a number between 0 and 1 if it's uniform?
Then just for ticks on each side.
Same number of ticks, right? Everywhere. Right? That would be, and this is some value, uniform probability. Right? And depending on how I cut it up, let's say I only want to show you the integers. So there's no integers. Let's say I only want to show you 0.1, 0.2, right? Then the probability of getting 0, 0.1, 0.2, or any of those numbers in between is all of the numbers divided by that. So it'd be 1 divided by the total number of numbers that you could have. That's quite tricky, obviously, on a computer. You can see why that would be, because you could have infinite numbers in between. But this is a uniform distribution. How do I shape it so it's non-uniform?
2 has like 1 higher.
Well,
Like its probability.
this is still X, right?
Mhm.
So if I hit it with a function, some function f of x, but in this case, I'm going to call it p of x, that is going to shape the distribution. So let's take something like e to the t over tau, right? And it's large over here and goes down over here, right? That's going to shift the numbers to the left. And to create an uneven, an ununiform distribution, you can just feed in a uniform distribution to a function and then compare it in an interval, right? Does it make sense what I'm asking so far? So I could say I want to compare this interval of x plus dx. Okay. What's the likelihood that I get some answer in here? Well, if it was just uniform, it would be the same everywhere. But if I'm first feeding it into here, then I'm much more likely to get these numbers. And it turns out as I run that over and over and over, the probability that I get these numbers between x and x plus dx is going to end up matching the shape because I've designed it to match the shape, right? Okay, it's the same thing that you might get. So instead of, let's say I want to go from 0 to 1, let's say I want to go from 0 to 10. Well, I just take my input and I multiply it by. I want to go from 0 to 1 to 0 to 10. You just multiply random by 10, right? That's going to give you the same thing. So all you've done is you've just stretched the x, right? Or if you want to shift it over, let's say you want to start at 3 and go to 30, what would you do? What? 3 to 30, there is a times 10 in there, good, but you have to do something first. So 0 has to go to 1, right? And then you can multiply it by 3. You see? Okay. So you can keep playing with how x is distributed, and then you can either bunch it up or stretch it out, and you're going to get different values for x along the way. Anything more you wanted to add, David? This one here?
They again do the financial from equation 10.7 and you apply that to equation 10.11. However, that isn't solvable, so what they do is they imagine it having different variables, x and y, and solve it in the forward coordinates.
Yeah.
From there, they define the forward coordinates, how you define this, and y in forward coordinates as r cosine theta, r sine theta. That's pretty much all.
Yeah. Well, for this one here, I think it really helps to sort of use this example, right? Because, did you read this one here? Do you want to talk about it or you want me to talk about it? Okay, so in this example here, what we do first, we're imagining bouncing. So this is an alpha particle, which is helium, bouncing off of a nucleus, and it's being deflected by electromagnetism, and it sort of has this angle, right? And so the question is generate two random numbers. Okay, can we do that? R is the square root of this thing, and this random, 1 minus random, that's the same way that we wrote it down here, right? No, wait, where'd it go? Yeah, it's here. R squared, we put it in here, 1 minus z, where z is our random number, right? And similarly for theta. And you create these two random numbers, and just based on those r and theta, the distribution that you're going to get is going to be Gaussian, right? And once you do that, you can ask the question, okay, if B, and for this particular problem, you're comparing whether or not this impact angle, which is like your closest approach, is smaller than some value and how you're going to get scattered, right? And once you've created these two, you can just run it and see how many were reflected out of a certain angle. So how many were deflected away, right? That's about it. Yeah. Monte Carlo integration is a topic we're not going to get into, but if you are interested in using random numbers to solve problems, it is a very unique set of techniques. So at the very beginning of this, they talk about something called Brownian motion. Do you know the history of Brownian motion? I'm going to go on another tirade really quick. What? What is Brownian motion responsible for? That's right. Brownian motion is responsible for the discovery of atoms. So before people thought about whether or not electrons and nuclei were individual things going around one another versus some amorphous soup. Okay. And Brown, who's a person, was watching pollen suspended in water. And he would watch it move around. And it looked like it was bouncing off of shit. Right? And making this random motions. And these random motions are due to the collisions of that pollen molecule with the water molecules, literally hitting off of each other. And therefore indicating that these are not amorphous soups, right? But real hard things that they can scatter off of, right? So in that process, when we think about Brownian motion, it's like we talk about, have you ever heard of the drunkard's walk? Okay, the drunkard's walk is an example of Brownian motion. Uh, it's just called that because it's like someone who's walking with no thoughts. Okay, so at each step, we're going to make a new decision. And it's very straightforward. Ready? Here's the Brownian motion. Or sorry, here's the drunkard's walk. You're going to do it, and I'm going to be the drunkard. So we're going to make me move left if you move your right hand, and we're going to make me move right if you move your left hand. So ready, everyone, on the count of three, you'll do 1, 2, 3, and you'll all raise your hands, and I'll count. Okay? 1, 2, 3. Okay. 1, 2. Okay, so everyone wants me to move this way. Okay, now put your hands down. 1, 2, 3. Did everyone just do the same hand? No? Okay. This way. Okay, and you can keep doing that at every step. You either move left or right. And every once in a while, right, a couple lefts will build up, and then a couple rights will build up. And then some lefts will build up, and some rights will build up. And on average, you'll stay where you're supposed to, right? As long as the distribution of going left is equal to the distribution of going right. But if I add a second dimension, if I can move forward and backwards, then I certainly won't end up where I started, right? And you can play this experiment at home. This is a fun one to do with your friends. Okay, you blindfold them. And you ask them only to take a step forward, backwards, left, or right. And you see who can be the best at staying on, say, a small square. Right? And you can do this with multiple people. They will just randomly walk around the room and they'll end up very far from where they started because that's what the Brownian motion does. So the Monte Carlo simulation takes advantage of this. It basically imagines a bunch of little walkers and it says, okay, let's imagine that we sample from a distribution of potential outcomes. And we take this outcome and we simulate it. And then we take this outcome and we simulate it. And we compare all of these different simulations. And based on the probability of each of those, let's say this one over here is more likely, then the simulation associated with this outcome is the more likely one. But these ones over here, they're also potentially possible. And this is how, for example, weather modeling occurs. So if you've ever looked at a hurricane track, they don't provide one track. They provide like 9, right? And they seem to diverge with time. Very close the beginning of the simulation, but a week out, they've all gone into different directions. And that's because each of the simulations, they start with slightly different parameters, assuming that we don't know information about the atmosphere perfectly. And so therefore, they're going to diverge after some time, right? Because they're truly random phenomena. Cool. So if you're interested, I would deeply recommend reading the Monte Carlo process, but you don't have to, because I know you're obviously very busy. Okay. So let's break up into groups. This is one of our last pair programmings. So pick your favorite person. No, just kidding. Pick anyone. And we're going to do random numbers. We're going to do the decay of, I forget what the decay is. The decay of bismuth to bismuth. From big heavy bismuth to slightly lighter bismuth. And if you love atomic physics, that's great. But if you don't love atomic physics, let me just introduce you to some numbers here. The 213, this is the weight. Okay. So 213 bismuth is heavier than 209 bismuth by 4 units. And that 4 units is essentially both 2 neutrons and 2 protons, right? That's what keeps it together. And so in this process, you are losing, when you go from 213 bismuth to 209 thorium or to 209 lead, you're losing a helium atom, an alpha particle, right? And then when you go from 209 lead to bismuth, you lose something else. And if you really care about the modern physics, you can look up what that object is. Hint. It's not weight, right? It's 209 to 209. So something else has to change, right? And in that process, you do learn a little bit about the table of elements because they are deeply connected by transitions between different properties, right? Just collections of these protons and neutrons. You plug them together, you call them one thing. You change one of those neutrons to a proton, it becomes something different, but it does not affect the total weight, right? Okay. So in this circumstance here, you're going to start with the bottom transition. And I would recommend that you just go back, do this with a friend. Before you write this code, think about how you would write this, right? And then compare it because you'll use that same code to do part A. It's almost identically part A. Part B is pretty good, right? You just add a little complexity. And part C, all of you will get upset. I promise. Okay? Yeah.
When lead goes into bismuth, is there gonna be mass that transitions because the electron has mass or no?
They are basically the same atomic weight. There is a small weight difference, but is it an electron lost or is it a negative electron gained? I will not comment on that. Okay. Everyone happy? Or as happy as they can be for the last week? Okay, let's break up into groups and we'll get started.